The title of this talk is Certificate Games. I'm Anupa Sunny, and this is a joint work with Sourav Chakraborty, Anagal, Sophie Laplante, and Rajat Mittal. In this talk, we will look at some complexity measures of Boolean functions. In particular, we consider a two-player game where the players are not allowed to communicate. Based on their probability of winning this game on a function, we introduce a complexity measure for this function. We will compare this new measure with existing complexity measures and see how it fits in the landscape of complexity measures. Let me first introduce the game. We have a Boolean function f, which takes an n-bit string as input and maps it to 0 or 1. The players Alice and Bob are not allowed to communicate, and this is illustrated by placing a wall between them. Alice gets his input x, which is mapped to 0 by the function, and Bob gets his input y, which is mapped to 1 by the function. Now, Alice has to produce an index I between 1 and n as her output, and Bob has to produce an index j. They win this game, which we call a certificate game, if the indices they produce as outputs match, that is I is equal to j, and their inputs differ at this index. That is, xi is not equal to yi. Note that this is a zero communication game. That is, the players are not allowed to communicate. Based on the certificate game that we introduced, we define the certificate game complexity measure as the inverse of the winning probability for the best strategy and the worst case input pair. We consider 4 variants of this complexity measure based on the strategies that the players are allowed to use. The first of these is the CG measure, where each of the players has access to their private sources of randomness. The second is the CG pub measure, where the players can use a shared source of randomness. Next, we have the CG star measure, where the players are allowed to use shared entanglement. And lastly, we have the CGNS measure, in which they can use any non-signaling strategy. That is, Alice's strategy has to be independent of Bob's input, and Bob's strategy has to be independent of Alice's input. Since any private randomness strategy can be simulated using shared randomness, and since shared randomness can be simulated using shared entanglement, and non-signaling strategies subsume all of these, we have the string of inequalities as shown here. Certificate games are related to various concepts that have appeared in the literature. They are similar to Kachma-Victorson games, except the players are not allowed to communicate here. They are also related to non-local games, but the objective function is different here. So why do we consider CG measures? The most important reason is that when we consider its behavior with respect to other measures, it fits in nicely in the landscape of complexity measures. Here I have this diagram which illustrates the relations between some of the known complexity measures and the newly introduced CG measures in red boxes. An arrow from A to B indicates that A is asymptotically larger than B. The certificate game measures are easy to bound above due to their game formulation. And on the other hand, certain variants such as the public randomness variant CGPUB and the non-signaling variant CGNS have dual formulations in terms of linear programs, which help give lower bounds. The outline for the rest of the talk is the following. We will focus on relating certificate games to well-known complexity measures. The definitions for these measures are included in the slides for completeness, but I will skip through them due to time constraints. If you would like to recall any of these definitions, kindly pause and proceed. We will begin with an upper bound on the CG measures with respect to the well-studied certificate complexity. As a warm-up exercise, we show that the private randomness variant CG is at most a product of 0 certificate complexity and 1 certificate complexity. A useful property of 0 certificates and 1 certificates is that any 0 certificate and 1 certificate should intersect at some position. That is, there should be an index which is assigned conflicting values by the 2 certificates. Let Cx be a smallest size 0 certificate for x and let Cy be a smallest size 1 certificate for Y. Let us consider the following protocol using private randomness. Now, Alice is given an input X with the function value 0 by the verifier, and Bob gets Y with the function value 1. They send their outputs to the verifier, who checks if their outputs satisfy the winning condition or not. Now, Alice and Bob take their respective certificates and randomly pick an index that is assigned a value. Now, when do they win if they use this strategy? They win when they pick an index common to both the certificates and that is assigned conflicting values. With what probability does this happen? Now, Alice picks this common index with probability at least 1 over C0, and Bob picks the common index with probability at least 1 over C1. Thus, the probability that their outputs match and is correct is at least 1 over C0 times C1. The private randomness variant, CG, is at most the inverse of the winning probability, which is bounded above by the product of C0 and C1. Note that this bound is tight. For instance, we have the parity function whose 0 certificate complexity and 1 certificate complexity are n, and we can show that CG of the parity function is n squared. Now, can shared randomness help? What we have so far is that the private randomness variant CG is at most the product of 0 certificate complexity and 1 certificate complexity. It is straightforward to see that the public randomness variant is always bounded above by n. For instance, we could sample a random index t using shared randomness, and both Alice and Bob output the index t. With probability at least 1 over n, this is an index where their inputs differ and they win. But can they do better with shared randomness? We will focus on this in the next few slides. We will start with an example of the tribes function to illustrate the power of shared randomness. We will generalize this protocol to get a better upper bound on the public randomness variant of CGPub. In particular, we show that CGPub is at most certificate complexity, which is the maximum of 0 certificate complexity and 1 certificate complexity. Let us now come to the tribes function. It is defined as a composition of the odd function on square root n bits with the AND function on square root n bits. In other words, we can think of the input as being divided into root n blocks of size root n each. To each of these blocks, the AND function is applied and their outputs are sent to the OR function. Now, according to our setup, Alice gets an input X, which is evaluated to 0 by the tribes function. What does such an input look like? Since the output is 0, the input to the OR function should be all zeros. Since each of these input bits is the output of an AND function applied on a block, there must be at least 1 0 in each of these blocks. Now, Alice does the following. For each block I, she picks an index AI where the input bit is 0. That is, X of I, AI is 0. For simplicity, we consider the special case where all of the AIs chosen by Alice are distinct. Thus, Alice has a bunch of AIs from A1 up to A root n, which are all distinct. Now, what does Bob's input look like? Bob has an input Y, which evaluates to 1. This means that there is an input bit to the OR function, which is 1. Since this input bit is the output of an AND function, the corresponding input block should be all ones. Thus, Bob has at least one block, which is only ones. Bob picks one such block and calls it B. Since every position in Bob's block B is 1, and since Alice has a 0 in each block, the index B, AB should have a 0 in Alice's input and a 1 in Bob's input. If Alice and Bob are both able to identify this position, they win the certificate game. Now let us look at the following protocol, which uses shared randomness. Alice and Bob pick an index T between 1 and n using shared randomness. Bob knows that his output must come from within his block B, and so he outputs B, T. Now Alice searches all of her AIs for an AI which is equal to t, and she outputs I, t. Now both of them output b, ab if the randomly chosen t is equal to ab, that is, when t is equal to the index where Alice has a 0 in the bait block. With what probability does this happen? Since t is chosen randomly, t equals ab with probability 1 over square root n. So both of them output b, ab with probability omega of 1 over root n. We have considered a special case where all of the AIs chosen by Alice are distinct. We will see that we can relax this constraint using hash functions when we generalize this protocol to all functions. Now, what we have seen so far is that the public randomness helps in the tribes function. It is easy to check that the 0 certificate complexity and 1 certificate complexity of this function are root n. Using our upper bound for the private randomness variant, we have CG of tribes to be at most n. A matching lower bound also exists, which gives CG of tribes to be theta of n. We have seen that public randomness gives you a significant advantage, that is, CG pub of tribes is O of root n, and a matching lower bound also exists. Using similar ideas, we will show that CG pub of a function is asymptotically at most its certificate complexity. Firstly, let us pick a set S of size certificate complexity of F. Let Cx and Cy be smallest size certificates for X and Y respectively. Now, using shared randomness, we select a random hash function H that maps the set of all indices to the set S. We also select a random element Z from the set S using shared randomness. Now, Alice looks at the set of indices that are assigned values in her certificate, and she checks if any of those indices are mapped to Z by the hash function H. She outputs one such index randomly. Bob does the same with his certificate. Now let I star be an index that is common to both the certificates and is assigned conflicting values by them. What is the probability that Bob and Alice output I star? For this, two events must happen. The first is that H maps I star to Z, and the second is that no other index in their certificates is mapped to Z. Since H is a random hash function, the first event happens with probability 1 over size of S, that is 1 over certificate complexity of F. We can also show with constant probability that no other index is mapped to Z. This shows that CG pub of a function is at most its certificate complexity. An argument with weights gives that CG pub is bounded above by expectational certificate complexity, which is a smaller measure than certificate complexity. We will now move on to another complexity measure called the randomized query complexity and see how CG pub is related to it. Here is the definition for the query complexity measure. We will now show that CG pub of a function is at most randomized query complexity. In a decision tree, let us consider a path that leads to a leaf labeled 1 and a path that leads to a leaf labeled 0. Any two such paths must necessarily diverge. Here they diverge at the node x2, that is, any two inputs that lead to these paths must differ at the second bit. The players win the certificate game if they are able to identify this node. Using shared randomness, Alice and Bob sampled a deterministic decision tree according to the probability distribution given by the optimal randomized decision tree. Now, the probability that this decision tree is wrong on X is at most 1 by 3, and the probability that it is wrong on Y is at most 1 by 3. This means that the probability that it is wrong on either of them is at most 2 by 3, and thus with probability at least 1 by 3, the sample decision tree is correct on both X and Y. Now, using shared randomness, Alice and Bob sample a level T between 1 and the randomized query complexity of the function. They output the tth index queried by the decision tree on their respective inputs. Now, with probability at least 1 over R of f, t corresponds to the node where the paths diverge. Since CGPub is at most the inverse of the probability that the outputs of the players match and are correct, we have that CGPub is at most R of f. Now, at this point, it is natural to ask if the quantum variant of the certificate gains, CG star, is at most the quantum query complexity Q of f. However, this is not the case as the OR function has quantum query complexity theta of root n. We shall see in the next few slides that CGPub of the OR function is theta of n. We will now show a lower bound on the smallest certificate gains measure we consider, namely the CGNS measure. We will start with an example and then show a general lower bound in terms of another complexity measure called the fractional certificate complexity. But first, let me formally define CGNS strategies. We will use P of I given xy to denote the probability that Alice on input x outputs I when Bob has input y. And similarly, we define P of j given xy. We say that the probability distribution P corresponds to a non-signaling strategy if Alice's output does not depend on Bob's input and vice versa. That is, the probability that Alice on input x outputs I when Bob has input y is the same as the probability that Alice on input x outputs I when Bob's input is different, and similarly for Bob. We will show that CGNS of the OR function is at least n. We prove this by contradiction. Let us assume that the winning probability of the CGNS game is greater than 1 by n. This will imply that the players can send information without communication. Now, suppose Bob wants to send a number between 1 and n. Alice chooses the all zero string as her input. Bob picks the string with zeros everywhere except at the ith place where it is 1. They can now run the zero communication game order of n times and take the majority output. Alice now learns some non-trivial information about the number I that Bob wanted to send, but this would violate the non-signaling principle. Thus, by contradiction, we have the CGNS of OR is at least n. We will now see that CGNS is bounded below by fractional certificate complexity, which is a measure for which multiple formulations have appeared in the literature. The proof can be sketched as follows. Let P be the probability distribution given by an optimal CGNS strategy. Since P is non-signaling, we can take marginal distributions to be P of I given x, since they are independent of the other player's input y. Our idea would be to use the probability distribution P to construct weights Vxi's, which are feasible solutions for the fractional certificate complexity linear program. We will use the following important properties or inequalities in our proof. The first is that the probability that Alice outputs a correct index I is at least the probability that both of them output a correct index I. The second is that if delta is equal to 1 over CGNS of f, the probability that both output a correct index I is greater than or equal to delta. Now we will construct weights for FC using P. We choose Vxi's to be P of I given x scaled by 1 over delta for all x and for all I. Using the inequalities given earlier, we can easily show that this is a feasible solution. We now have that CGNS is at least FC. We will now consider the single-bit versions of certificate gains, which are played on restricted inputs. Here are the definitions for the complexity measures, sensitivity, and spectral sensitivity, which we will show are related to the single-bit versions of certificate gain complexity measures. Single-bit versions of certificate gains are played on restricted inputs x and y, which have different function values and have a Hamming distance 1 between them. We show that the public randomness variant characterizes sensitivity exactly and the public randomness variant characterizes the sensitivity exactly, and the private randomness variant is equal to the square of the spectral sensitivity. Now we bring back the diagram, which illustrates the relations that we have discussed in this talk and more. Some of the important open questions are the following. Can we come up with a better upper bound for CGPub in terms of the single bit version of CGPub? In particular, is CGPub at most square of CGPub 1? A positive answer to this would resolve the quadratic sensitivity block sensitivity conjecture. We could also ask if we can come up with a better upper bound on the zero error randomized query complexity R0 of F in terms of the square of CGPub. Thank you.